Hello. Today we will talk about a new topic. One of the important tasks of numerical analysis is solving algebraic equations. Now we know algebraic equations, at least we met them before. We learned how to solve linear equations in elementary school. Then we learned how to solve quadratic equations. And that's about it. There is no other group of equations that you would learn how to solve, which is a little bit surprising perhaps. But the reason is simple. Algebraic equations are in fact very hard to solve. And by solving, I mean finding root using expressed with algebraic expression, essentially. So here is an example. Cosine x is equal to x. That's a very simple equation. And when you look at the graphs of these two functions, you can see that they intersect. So definitely this equation has a solution. I can see it right here. But surprisingly enough, I cannot express this solution with some algebraic formula. So from the theoretical mathematics point of view, this root is unreachable, but we need to know it sometimes in practice. I mean, there are many algebraic equations which are very useful in applications. So how do we get this root? Well, we have to turn to numerical analysis for some approximation. And when we are talking approximation, we are talking about precision. So somebody specifies precision for our calculation, for the result, or a tolerance. And now we are trying to produce some approximation of this root so that it doesn't differ from the actual value by more than epsilon. Or perhaps we want the error to be less than epsilon. Sharp or not sharp inequality, that doesn't make much difference. So how do we find it? And we start with a little trick. With every equation, you can move everything to the left and change it into such a form. So we are going to focus on the question of finding roots of functions, which is the same question, definitely. And on the slide, you can see a little friendly reminder of a root, but I'm sure that you know the notion, so there's nothing surprising. So we have a function, and we are looking for a root. And the first good question is there a root? And already this question is surprisingly difficult to answer. There is no reliable procedure that could answer it. And essentially, we are left with some hints. Some of them are very good. Here is one of them. Here is a theorem. Let's decipher it. We have a function which is given on an interval AB. It's a closed interval. So here is my situation. Interval AB. And there's a function on it. So far, so good. And there is a mathematical condition, fa times fb is negative, but this translates into saying that the values at the endpoints have opposite signs. Let's say like this. So that's the situation. I substituted a, substituted b, look at the signs, and of course one of them can be 0, and then I found the root. But we are not going to be that lucky. So let's assume that the signs are distinct, and then common sense suggests that actually there should be a root somewhere in the middle. This is how we imagine it. But of course, we know from analysis that things can get more interesting. This is a little bit boring. So for instance, we can have a function which is not continuous. And then there is no root, so we have to be careful. And that's the third line in this fact. If f is continuous on the interval AB, then there must be a root. Wonderful. So in this way, we somehow correlate the root or cornered it. We have it bracketed. That's a good mathematical name for it. We have the root bracketed. We know for sure that it's there. Of course, a good question is how to find a and b. And the answer is, well, essentially by experimentation. You take your function and you start putting numbers in, and you are hoping that the sign will change sooner or later, preferably sooner. Or perhaps you can plot, perhaps you can make a rough plot of the function and then you can guess. But none of these tricks is reliable. There is always a function which causes trouble when you try this or that approach. So as I said, there is nothing guaranteed here in this field. One has to be lucky a little bit too. Also, there are situations where this theorem cannot help fundamentally. Let's say this one. I have a function here, and quite obviously, the way I draw it, It has a root here. But we cannot corner it, we cannot bracket it using this method. Because no matter how hard I try, the sign will never change. And that's not a very ugly function, that's a nice function, and it causes troubles. You can imagine that it's y is equal to x squared, for instance. Now, when you see a shape like that, it means that the root here has higher multiplicity. In this case, it would be even multiplicity, multiplicity 2 or 4 or 6 and so on. And roots of higher multiplicity, they cause troubles in this field of numerical analysis. We will see it repeatedly. So it's not so surprising that a root of even multiplicity is not very pleasant. Anyway, so let's assume that we got lucky. We have a function, it's continuous, and we found two numbers where the signs change. So what do we do next? Most likely, there is some region of uncertainty, and probably it's larger than epsilon, so we are not happy yet. Well, there is a very simple idea. I look at this interval and I find the middle. And then I substitute into my function and I get a sign, let's say positive. Yeah, positive is a nice idea here for this picture. Of course, if we get 0, the procedure ends. So let's assume it's not 0, then it must be positive, negative. And whichever alternative it is, there will always be one half where the sign changes. In this case, it's the right half. So right now, again, I bracketed my corner, my root, but this time the bracket is smaller. So the root is identified with better precision. And of course, I can continue in this way. So I will identify the middle of this segment. How do I identify the middle, by the way? Well, it's just the average of the endpoints. So this is not really a problem. I substitute, well, let's say negative. Looks like a good idea here. So if the sign here is negative, I compare the three signs, and I see that I should go here into this half. And I keep going like that. I take the middle, substitute, well, let's say positive, and so on. And you can see that I'm getting the root cornered with better and better precision. And since the precision is improving at every step, essentially the uncertainty is halved. Sooner or later, I will have the root cornered with enough precision. So that's an outline of an algorithm. It has an official name. We have to introduce some mathematics. So what we do essentially, we are going to construct two sequences of points, the left endpoints, the right endpoints. That's the starting point, so let's say A0 and B0. That's a good name. Then we calculate the middle, let's say M0. That's a nice name for middle. And we decide that this point will be A1 and this will be B1. And then there will be middle, M1. This becomes A2, this becomes B2, and so on. So there are two sequences which are potentially infinite, but of course we will cut it off at a certain point. And now let's have a look at the algorithm. I didn't use any computer language intentionally, because we don't want to get tied to some computer language. So it's written in words. Let's see, given, what's the starting point? We have a continuous function on interval AB. We have a tolerance epsilon. And we assume that we got lucky and found places with opposite signs. So far, so good. So we set A0 and B0 as given. And then we construct the midpoint in step 1. And you can see that the first formula is just the algebraic average. I will get to the second formula shortly. And then we compare the signs of the old endpoints and the midpoint. And we are looking for the change of sign. And in part 2, we first check, perhaps we found the root by accident. And then, of course, the algorithm stops. And if it doesn't stop, then we have to say what is the official output. And if we are at a certain stage, then it makes sense to put the midpoint as the official output. So for instance, if we stop here with our algorithm, if we are happy with this precision, then people usually don't ask for an interval as the answer for the root. They ask for a number. So the best guess, if you know that the root is here, would probably be the middle. So that would be the official output. And here the official output would be middle 2 and so on. This makes sense. So these numbers are the official outputs from each stage. And if you are not lucky, if you are not happy with the size of the bracket, which is the condition on the line marked 2, then we keep going. So this algorithm is not really difficult. Let me move it up a little bit. And you can read it at your leisure. The important thing is to understand the workings of it and being able to apply it. So let's try an example. Here is a function which I decided to check on. It's a cubic polynomial. Now, there are formulas for roots of cubic polynomials, but they are not really friendly, and nobody really remembers them. So, let's try some guessing. Okay, my favorite number for substituting is 0. So how much of f0? f0 is -10. So right now we know that at 0, the sign is negative. Okay, how about some x, which I put in here, and I get a positive number? We know that cubic power grows quite fast, so I put something really huge there. Let's say f5. How much is a 5? 125 minus 120, 110. Nice number. But I don't care. The only relevant information is that it's positive. So right now I can set up my calculation, and I would say that A naught is 0, B naught is 5. And if I decided to stop right here, then the official output would be M0, which is the average, which happens to be 2.5. Okay, let's say that I'm not happy with this answer, so I keep going. I take this average, this midpoint, and I substitute. Okay, let's try it. 2.5 squared is 6.25, and I still have to multiply it by 2.5. 6 point something multiplied by 2.5 is 12, 15, 15 and a little bit. 15 and a little bit minus 2.5 is 13 and a little bit, minus 10 is 3 and a little bit. Positive. I'm lucky that I didn't get close to 0 yet. Then I would have to really do precise calculations. But this I can guess or guesstimate. So in the middle, the sign is positive. So what does this tell me? Well, this tells me that I should focus on the left half. So A naught is still 0, A1. While B1 becomes 2.5. What's the official output at this stage? Again, I look in the middle and it's 1.25. If I'm not lucky, I keep going. I substitute 1.25, and well, I'm not going to calculate it anymore. I could guesstimate. 1.25 is definitely less than 1.5. 1.5 cubed is about 3 something, minus 1 is 2, minus 10 is -8. This is negative. But of course I would use calculator for it or a computer, which is a good idea. Let's ask computer for that. But before we do it, when we do calculations like that by hand, we sort of get a good understanding of the method. So this bisection method, you can see that it's very simple. You just keep substituting into your f. What can go wrong? Well, nothing much. So that's a very nice calculation. By the way, we talked about numerical errors. Of course, you can have numerical errors here, but that's not a problem of the procedure of the bisection method. That's a problem of calculations of f. So that's a slightly separate problem that we should worry about, of course, but it's not a question for the method now. There is one interesting place where one could run into trouble due to numerical mistakes, and that's the calculation of the midpoint. If I use the formula 0 plus 5 divided by 2, this can get into trouble if those numbers are really close and the round of errors start playing. It can happen that when you do this calculation, you add it and you divide by 2, you get a number which is actually outside of this range, which sounds weird, but this can happen. So there is an alternative formula. When you look at there, step 1, let mk is equal to. The alternative formula is actually more resistant to numerical errors, to round of errors. So there are some little things that one has to be careful when you are implementing this procedure. But otherwise, it's fairly reliable, it seems. So let's try some example. we switch to maple. I'm going to enter the function x cubed minus x minus 10. Yeah, that's the right one. And now I will ask for the root of it. Initial interval is 0, 5. That's exactly what I had over here. The method is bisection. And the tolerance, that's too much for the start. Let's try this one. That's 10 to negative 4. Okay. Well, perhaps like this. Let's have a look what's happening here. So in this column, we can see A's. Here we can see B's. And the second interval is 0, 2.5, which is exactly what we have here. And the third interval is 1.25, 2.5, which is something that we would obtain here. We would pass to this interval. So this seems to make sense. And after some 15 iterations, we got the estimate of the root, which is here, with precision 0.0001, which is 10 to negative 4. That's very nice. Do I want to play with this later on? I think I want. Okay, let's have a little chart here. So when the precision is 10 to negative 4, then the bisection method required 15 iterations. The number of iterations is obviously some sort of measure of speed of an algorithm in this case. Now, what can we say about this method? So let me put it here. It's a bisection method. And perhaps I will put a little remark here. This is a typical example of a bracketing method. Bracketing methods are methods where you have the root cornered and you never let it go. So this bisection method is something like prototype or the simplest method which uses the bracketing principle. Now, features, core features. It's reliable. What can go wrong? I mean, apart from perhaps numerical problems, nothing. The method itself does exactly what it's supposed to. It will corner the root with arbitrary precision. Nothing wrong there. Second important feature, we have a control over error. Well, let's talk about error for a while. So let's say that we stopped at a certain stage. So there was the official outcome, mk, and I'm asking, what is the error? Well, the error is just the difference between the actual root and our guess. And I will look at the absolute value. Now, where does the mk come from? Well, there must have been an interval called ak and bk, and mk is the middle of it, the midpoint. Now, we know for sure that the root is somewhere here. So if we offer mk as the approximation, then the largest error that we are making is just half of this interval. So the actual error is less than or equal 1/2 of bk minus ak. Which is nice, but let's pass to another step. The interval bk minus ak, the length of it, is just half of the previous length, because at every stage the length of the interval is halved. So I can introduce another 1/2 here, and there will be bk minus 1 minus ak minus 1. And I can keep going like that. I can trace my way all the way to the start, and I obtain b naught minus a naught. And then there will be 1/2 to some power. Now I never remember the power. Let me think about it. If it's happening here with 0, it should be k plus 1. Either k or k plus 1. So I always have to think about it. For instance, if we stop at the first stage, which is m1, then the error for M1 will be the size of interval, half of the size of the first interval, which is 1/2 of the original. So this fits. Yeah, there is an extra 2 in the denominator. So the error is nicely controlled by data which we have available. We know the interval that we started with. So this number is known. And also we know how many iterations actually passed, how many we used before we got to MK. So we can estimate the error very nicely. That's the control over the error. Very nice. We can even predict how many iterations we have to take before this bound on the error becomes sufficiently small. We can just simply put as an equation this, and we solve it for k. And that's not difficult. You just move this to the right, you move epsilon down, you take logarithm, you get the answer. So this is actually also a predictable algorithm. Very nice. The third property, which I'm interested in, is that it's slow. What does it mean that it's slow? Well, it means that you have to do many, many calculations before you reach the precision. How do I know? Well, let's have a look at the experiment. Now, one measure of the speed or one measure of quality of our approximation is practical. We just look at the approximation and we ask how many digits are actually guaranteed. How many of them are correct for sure? And when I look at the error, I can see the correct digits by zeros in the error. So let's have a look over here on the right. This test is actually this value. It's the upper estimate. That's very useful. Let's call this number EK. So the actual error is capital EK and the estimate is little ek. Now, when we look over here on the test, we can see these little zeros here. So at this stage, the upper estimate suggested that the first decimal digit in the approximation is already correct. Now, in these next lines, it seems that 2 digits should be correct, and then 3 digits. And when we look at it, how many iterations did it take to improve our precision by 1 digit? That's a good question. And we can see over here in these 3 rows that it took 3 iterations. And then we got a new digit. Here it took 4 iterations, then we got a new digit. Then 3 iterations. So it went like 3, 4, 3 iterations to get new digits. Let me ask for better precision. Oops. 10 to negative 7. And let's run it again. This time it took 25 iterations. And let's have a look at it. So we stop here. 3 digits, 3 digits, 3 digits. That's okay. Then 4 digits, 1, 2, 3, 3 iterations again. And then I look here and I get 1, 2, 3, 4 iterations for the next digits. And then 3, and so on. Now, here's a little problem. What we see here is not the actual error, but it's the estimate for the error. And the actual error could be smaller, or perhaps not, we don't know, but we will return to it in a second. When we look at the estimate, we can see that improvement by 1 digit is given by a certain number of iterations, which seems to follow an interesting pattern. And this pattern, there is a good justification for it. Let's have a look at it. It somehow relates to the question of relative error, of course, because the number of digits that we trust is closely related to the relative error of our approximation. So we should be actually asking for ek divided by the actual value, which is r. But let's first have a look at this. The estimate, by our reasoning, satisfies an equation like that. At each step, the estimate for the error gets halved. We already noticed it. Now, if we want to pass to relative errors, of course, we don't know the actual error. But again, we can ask for the estimate for the relative error. So we just divide each side by r, which is the actual root. And when I do it, then this is the estimate for the relative error, and this is the estimate for the relative error. And this is, by the way, one of the reasons why we don't really talk much about relative errors when analyzing algorithms. If we find some relationship for the absolute error, then it usually carries over to the relative error as well. But anyway, when we look at this, we can see that at each step, the relative error, or the envelope for it, the upper bound, gets halved. Now, how do we improve precision by 1 digit? And we talked about it earlier. If you want to improve the precision by 1 digit, you have to lower the relative error 10 times. Now, what happens if we apply the bisection method 3 times in a row? The first time, you lower the relative error by 2, by the factor of 2. The second time again, second time again. So after 3 iterations, you get this estimate, which is almost 1/10. On the other hand, by the 4th iteration, the improvement in precision goes like that. So improvement by 10, which means an extra digit, happens somewhere between the 3rd and the 4th iteration, which is reflected in this pattern. One can go a little bit farther. What happens after 10 iterations? Now, 2 to the power 10, that's a popular number. It's 1024, which is approximately 1000. And the error is not too large. When I say 1000, it's almost precise. So we can see that after 10 iterations, we gain 3 new digits in our estimate. 3 new reliable digits in our estimate, which generally fits with this pattern. 10, 10, and so on. So the bisection method is predictable. That's nice. We knew it before. We talked about it, that we have control over the error. But it's also rather slow, in fact, because this is not very nice. 3 iterations, on average 3 1/3 iterations for each digit, that's too much work. Now, my function was very easy to evaluate, but if it's difficult to evaluate, we would have to evaluate 25 times some complicated expression, which would slow down our work. So we will definitely ask for faster algorithm. But before we go there, let me just make one little stop. We were not able to analyze the error itself, but we found an upper bound, and we analyzed the behavior of the upper bound. That's a very typical situation in numerical analysis. And in this case, the upper bound behaves in a very nice manner. At each step, it gets halved. So that's a geometric progression, a famous one. But that's the upper bound for the error. So the actual error can actually do something crazy here. It can go up, for instance. When you make the next step in bisection, the actual error can get larger. That can easily happen. But we are forcing it down at a predictable manner. So it must stay within the envelope, and the envelope is relatively nice. I have a code here, because actually I can figure out the root of this function also analytically using that formula that nobody remembers. And it's not a very nice formula. But anyway, I used it here to evaluate the actual errors, and I will go back to my original shorter run with shorter precision. And let's have a look at the error of these approximations. What you can see here in this column is the actual errors, and you can see that it's getting smaller, but sometimes it got larger over here in this step. And then it got really smaller, and then a little bit larger. So we can really see that the actual error jumps up and down. We can see it right here, so it can happen easily. But when you look at the zeros after the decimal dots, they are steadily growing. There is more and more of them, and there is this progression, roughly, which corresponds to 1/2k, which is actually considered to be quite fast, but for our purposes, it's not fast enough. So this is essentially all about the bisection method. So we saw some interesting features, and we saw that it's important to talk about the error, and it will be important for us later. Now, one of the reasons why this method is slow is that it doesn't really take into account the shape of the function. We never ask how the function behaves, how it looks like. We are simply plodding along regardless of the function itself. That's a big advantage because you cannot throw this algorithm off. It will just keep going like a steamroller or a huge tank. Doesn't stop for anything, but it's slow. So if you want to get a faster algorithm, we have to do several things. First of all, we have to erase the blackboard. Second of all, we have to start looking at a function. And it really helps if we change our point of view. So we will drop this bracketing approach, and we'll start from a new viewpoint. Let's go for it.